Welcome back, everybody. We got a good one for you today. It's differentials versus cusp forms. We are finally going to strongly tie together the notions of Hecke correspondences and Hecke operators. So, differentials. Let's let gamma in SL2 of z be a subgroup of finite index. Let's let pi denote the restriction to the upper half plane H of the natural map from H star, the extended upper half plane, including the rationals and infinity, to the orbit space of gamma acting on H star via fractional linear transformation. If omega is a holomorphic differential here, then you can pull it back through pi to get a holomorphic differential pi star of omega equals f of z dz for some function f on H. Now, which functions f on H will you get when you do this? The f that you get are characterized by the following three conditions. F is holomorphic on H. F of gamma z d gamma z equals f of z dz for all little gamma and big gamma. So f of z dz is basically gamma invariant. And then 3, let delta in SL2z and let m be a natural number such that f of delta evaluated at z of m times d of delta evaluated at z plus m just equals f of delta evaluated at z times d evaluated at delta of z. So in other words, f of delta, d of delta is periodic with period m, let's say. Now, such an m definitely exists by condition 2 combined with the fact that gamma is a finite index in SL2 of z. So you can definitely find such an m. Okay. Now, let's let f be the holomorphic function on the punctured unit disk d star given by f of delta z times d dz of delta z equals f of q to the 1 over m for z and h. Then f extends to a holomorphic function on d vanishing at 0. Okay, so we have kind of a cuspidal condition here. We want to be holomorphic and vanishing at the cusps. Okay, so these conditions should look somewhat familiar to you. They should look similar to the conditions for a function to be a modular function, although we have some stuff here with the derivative that's not obviously tied to that in here as well. Okay, but what you see with some work is from this discussion, if you return to the equation pi star omega equals f of z dz, and you allow omega to run over the space of holomorphic differentials on the orbit space of gamma acting on H star, then the function f that you get as omega runs through all those differentials runs over the space of cusp forms of weight 2 for gamma. Okay. And basically the weight 2 condition is hidden in this differential invariance here. Okay, references for this talk, by the way, probably CSS chapter 3 and Diamond and Sherman chapter 3. The past several videos have referenced Diamond and Sherman chapter 5, but I think chapter 3 is the relevant chapter here today. Okay, so let's specialize now. Let's specialize to the case gamma is just gamma sub 1 of n, the group we've been working with most. We'll write omega to the first sub x sub 1 of n for the space of holomorphic differentials on the modular curve x sub 1 of n viewed as a Q curve. We know we can do that. And we will write omega to the first sub x sub 1 of n kind of slash c for the corresponding curve over c. So in other words, it's view x sub 1 of n as a c curve and then look at its space of holomorphic differentials. Okay, the relation between the two of these is if you tensor up to c, omega to the first sub x sub 1 of n, you get omega to the first x sub 1 of n slash c. Now, what's going on here is you have a canonical isomorphism of vector spaces between S2 of n and omega 1 x sub 1 of n slash c. So weight 2 cusp forms for gamma sub 1 of n are in isomorphism canonically as complex vector spaces with the holomorphic differentials on the complex modular curve x sub 1 of n. Okay? In fact, it gets even better than this, though. To talk about how it gets better, we're going to have to talk about how correspondences induce operators on spaces of differentials. So let's let t equals z phi psi be a correspondence on a smooth projective curve x. Remember, that's just z equipped with 2 distinct maps to x that are non-constant. Okay. Then t, it turns out, admits an operator from the space of differentials on x to the space of differentials on x. And that operator is send omega to the phi trace of psi star of omega. What is the phi trace? Well, it's the trace on differentials associated to phi. I know that's not helpful. I'll describe it now. So you've got this map phi from z to x. You know by curves fields correspondence that induces an inclusion of function fields, let's say k to l, where K is the function field of X, and L is the function field of Z by pullback. Okay. Now, any alpha in the space of holomorphic differentials on Z will take the form alpha equals UdV for U and L and V and K. That's easy to show. And what you do is you define the phi trace of alpha to just be the usual field theoretic trace for the extension L over K of U times dV. And what's the trace of a finite field extension L over K at an element U and L? It's just the trace of the K linear multiplication by U map from L to L. So this is all standard like algebraic number theory stuff, or even just field theory stuff. Okay, so a correspondence on a smooth projective curve gives you an operator on the space of holomorphic differentials on that curve, period. Okay, and that operator is the trace. Let's specialize this to the Hecke correspondence, and we'll see something really awesome here. So the Hecke correspondence is TP, and the triple is X of NP, which is a special modular curve, phi P psi P, just recalling all the notation there. This is a correspondence on X sub 1 of N. So it's two maps from X of NP to X sub 1 of N given by phi P and psi P. Okay, if you apply the theory we just got done discussing, you find that there's an operator, TP, on omega 1 of X sub 1 of N. I wonder what it is. By extension of scalars, you get an operator TP on omega 1 of X sub 1 of N slash C. And it turns out, not only is there an isomorphism of complex vector spaces between S sub 2 of N and omega 1 X sub 1 of N slash C, but this isomorphism commutes with the action of Hecke for all primes P. In other words, if you were to do, let's call this isomorphism, I don't know, what do we want to call it? Psi. What I'm saying is, take the Hecke operator, T sub P, that acts naturally on S2N, and apply it to something there. So go TP of F, okay? And then apply psi to that, where psi is this isomorphism. The claim is you get TP of psi of F, where this TP refers to the induced operator on the holomorphic space of differentials induced by the Hecke correspondence on this side. So this is the Hecke operator. This is the operator on differentials induced by the Hecke correspondence. And so what we see after all is that the Hecke correspondence and the Hecke operators are describing one and the same thing, which is miraculous and it's really neat. And so the fact that weight 2 cusp forms for gamma sub 1 of N and differentials on the complex modular curve X sub 1 of N are the same in a very canonical way is really neat. It's very useful throughout this theory and these talks, but also just at large in the proof of Fermat's last theorem. And so we'll continue looking at this and make this kind of even better over the next couple of videos. So I'll see you then. Thanks for watching.